Hello everyone, in this video we are going to discuss about laterally supported beams.
Okay, so if you see in our previous session, we have discussed about the simply supported beam, okay, of I section, simply supported beam of I section with UDL. So in that case, we have discussed about the bending moment. So we know that from the strength of materials concept also, we know that for a simply supported beam with UDL, what is the maximum bending moment? It occurs at a center, and the maximum bending moment value is equal to WL square by 8, and the maximum shear force is WL by 2. But as here it is a working limit state method, so we have to multiply those external effects with a factor, that is 1.5. So after that, those moments are called as design factor moment and then design shear force. So design shear force V is equal to 1.5 WL by 2, and then design moment, okay, design factor moment is 1.5 WL square by 8. So this is what we have discussed. So now once if we look at into the I section, and the two, once if we recollect the concept of strength of materials, that is bending stress distribution and shear stress distribution. So I'm going to repeat it and repeat it again, and I'm going to draw those stress distribution for an I section. So if we take an I section, so obviously, as I said, this is a concept of strength of materials, but here it is required. So that is the reason we are going to repeat it again. Okay, this is the cross section of I. As we have discussed in previous class, so here the overall depth we are going to represent with H, and the depth of the web. Okay, depth of the web, we represent it with D, and the thickness of the web is TW, and then thickness of flange is TF. So that we have discussed. So now if we see the bending stress and shear stress variation throughout the depth of this cross section, first I'm going to show you the bending stress variation. So for this I section, here where the neutral axis lies. Okay, so here where the neutral axis lies for this cross section. So this is the neutral axis. So if you see the bending stress distribution, so this is how the bending stress distribution. So what you have discussed in strength of materials. Okay, so this is a bending stress distribution. Okay, this is a bending stress distribution. So if you observe, the maximum stress occurs at the extreme fibers. Yes or no? So the maximum stress occurs at the extreme fiber. And if you move toward the neutral axis, stress reduces. And at neutral axis, exactly at the neutral axis, the stress is zero. Okay, so it means from the extreme fibers, if we proceed towards the neutral axis, the stress decreases and it is zero exactly at the neutral axis. This is the bending stress distribution or variation along the depth of this I section. And if we observe shear stress variation, okay, so if you observe the shear stress variation for I section. So this is the shear stress variation. Top. And again, if we observe the shear stress variation, so if we observe the shear stress variation, so it is maximum at the neutral axis and minimum at the extreme fibers. And that too, if we observe the diagram, the variation diagram, the maximum part of shear exists only in the web area. Do you agree or not? The maximum shear stress. So if you see here, the maximum shear stress is in web. Agree. So now based on this concept, as I said previously, this is the concept of strength of materials. Okay. So now based on this concept, if we take in working stress method, of course we are not discussing the working stress method here. We are discussing only limit state method, but here that is required here. So in working stress method, we are going to assume that that 90 to 95% of shear is resisted by the web itself, and 90 to 95% of bending stress or flexure or bending moment is resisted by the flanges itself. So those are evident from the stress distribution. Okay, so once I repeat, if you see the bending stress distribution, the maximum is at extreme fibers. It means maximum stress is at the flanges only. And if you proceed towards the web, so that stress decreases and it is zero at the neutral axis, which is in the web. But if you take the shear stress, so it is a minimum in the flanges and maximum in the web. So based on that, in working stress method, we are going to take that, or we are going to assume that 90 to 95% of shear, 90 to 95% of shear is resisted by or taken by, web. It means we are going to assume that total shear is taken by web itself. So that is what the meaning of it. And 90 to 95% of flexure, or you can say bending stress is resisted by flanges. Okay, so this is what we are going to assume in working stress method, and we are going to take that or consider the total web is effective in shear and only flanges are effective in taking bending moment. But in that is in working stress method. But if we take in limit state method, okay, so far what we have discussed, that this 0.95 to 90 to 95% of shear is taken by web and 90 to 95% of flexure is resisted by the flanges. That concept is in working stress method. But coming to the limit state method, based on one criteria, we are going to classify that whether the total web is going to take the shear or not. Agree? Shear or not. So, but if we take in working stress method, purely or you can say bluntly, web is going to take shear and flanges are going to take bending moment. But here that is not the case. Based on one criteria, we are going to classify that. So that criteria is based on, or that criteria is classified as high shear case and low shear case. It means based on the shear force. It means this is based on this design factor shear force. Based on the design factor shear force, the design of laterally supported beam. Okay, the bending design strength or design bending strength of laterally supported beam is divided into two parts. That is low shear case and high shear case. Now, what is low shear case and what is high shear case? So again, for this also the strength of material concept is required. So in that strength of materials concept, we are going to discuss the distortion energy theory or shear strain energy theory. So according to that, the permissible stress in shear is Fy by root 3 or Fu by root 3. So simply, whenever we are going to take shear, then we have to use the root 3 factor. So if it is a yield, then Fy by root 3. And see, so far from the beginning of the boarded connections itself, wherever it is a shear is there or shear strength is there, we are using this root 3. Yes or no? So what is meant by root 3? That root 3 is based on that is a factor that is from a distortion energy theory. So Fy by root 3 or Fu by root 3. So mainly the structural steel fails by yielding, but the connections fails by rupture. So that is why if you see in the connections we have used Fu. But in the design of our structural steel, mostly we use Fy. But in tension members also we have used Fu. But other than that, but I'm telling you the most number of chances. Even in connections also, in butt weld we have used Fy. So as in a general, this is not an 100%, but 90% you can take it for granted that the design of connection is mainly governed by rupture failure, and the design of structural steel is governed by yielding. So that is why in the design we use Fy for structural steel, and for connections we use Fu, but that is not 100%. Okay, don't take it for granted. So whenever we are designing in shear, we have to take that particular stress, yield stress, by root 3. So this factor is based on distortion energy theory. So 1 by root 3. How much 1 by root 3? So if we simplify it, 1 by root 3 is nothing but 0.577. So we can approximate it to 0.6 Fy. So now high shear case and low shear case depend upon this. Well, how? So here I'm going to write if design factored shear force V. So if design factor force, which is equal to, in simply supported beam with UDL, which is equal to 1.5 into WL by 2. So the design factor shear force V, if it is less than or equal to 0.6 VD. So what is VD? VD is the design shear strength. VD is a design shear strength. VD is a design shear strength. So if V is the design factor shear force, VD is a design shear strength. So if this VD, if this V is less than or equal to 0.6 VD, then this is known as low shear case. This is known as low shear case. So as I said, this 0.6 is based on distortion energy theory. So if you want, you add this from, so I'm writing from distortion energy theory or shear strain energy theory. Or shear strain energy. Shear strain energy theory. So this Fy by root 3. So this is based on the distortion energy theory or shear strain energy theory. So based on that, we are going to divide the design bending strength of laterally supported beam into two cases. That is low shear case and high shear case. So now that is the condition for the low shear case. So if this design factor shear force is less than or equal to 0.6 of design shear strength, then it is low shear case. Obviously opposite. So what is the opposite? V. If the factor design shear force is greater than 0.6 VD, then it is known as high shear case. Then it is high shear case. So this is high shear case. So now what is the difference between low shear case and high shear case in the design? So in design, so after calculating the factor design force, okay, factor design shear force and the design shear strength. So if it is happen to be in a low shear case, then we are going to assume that total area of this I section is effective in taking bending moment. But actually from this diagram or in working stress method, we are going to take that, or we are going to assume that only flanges are effective in taking bending moment. Okay, and web is effective in taking shear. But if it is a low shear case, then we are going to assume that total area of I section is effective in taking bending moment. That is what low shear case. That is the shear force, the external shear force is less. So we are going to assume that so in web the shear is less. So web is also effective in taking bending. Okay, that is the assumption. But in high shear case, there the external shear force, or you can say the design factor shear force is greater than the 0.6 VD high shear case. So in this case, we are going to assume that only flanges are effective in taking bending moment. Only flanges are effective in taking bending moment. That is the thing we are going to take. That is the difference of low shear case and high shear case. I will write here. So here I write low shear case and high shear case. What is the difference in design? Low shear case. So we know which is called as low shear case. If the V is less than or equal to 0.6 VD, then it is low shear case. So in low shear case, total cross section of I is effective in taking, or you can say resisting. Effective in taking or resisting bending moment. Now, what is I shear case? In I shear case, in I shear case, in I shear case, only flanges are effective in resisting bending moment. In resisting bending moment. This is the concept. So before going into the design bending strength of a laterally supported beam, we should be clear about this low shear case and high shear case. So we should be clear about low shear case and high shear case. So based on which we are going to classify that, and all these concepts, that is a design shear force, okay, design factor shear force, and design factor bending moment, and everything. This stress distribution, that is bending stress distribution and shear stress distribution. So obviously this is a concept of strength of material. So take it on. So now let's start with the calculation of design bending strength. So actually this is for a case of laterally supported beam. So after this we'll see the laterally unsupported beam design. For laterally supported beam. Design bending. Design bending strength. We represent with MD. Okay, design bending strength MD. So now here there exist two cases. One is low shear case. Low shear case. We know that what is low shear case. So low shear case means total area of I section is effective in resisting bending moment. So that is low shear case. So what is the condition? If this V is less than or equal to 0.6 VD. See what is VD? Lateral explain. Okay. After completion of this design bending strength, we'll start the discussion of design shear strength. So there I'll explain how to calculate VD. So no worry. Okay. So as of now you consider VD as a design shear strength. Okay. Now in low shear case, the design bending strength MT is equal to, again, first of all, writing this formula based on strength of materials concept. Tell me what is the moment of resistance. See here, the bending strength is nothing but moment of resistance. So that we have made clear in the plastic analysis itself. Yes or no? Obviously, we have made it clear in plastic analysis itself. So what is meant by plastic moment? Plastic moment is the maximum moment of resistance or maximum moment carrying capacity of any cross section. So that is the plastic moment. So after that, that cross section will not have any moment resisting capacity. That is plastic moment. So likewise here the design bending strength is also nothing but moment of resistance. So now tell me what is the formula in pure flexure. So if you see the formula in pure flexure, that is M by I is equal to F by Y is equal to E by R. So if you consider the first two terms, so from this M is equal to F into I by Y, it is Z. Agree or not? It is Z. So this is the formula. So bending strength, design bending strength is equal to stress into Z. Z is the section modulus. Clear? So based on this Z only, we are going to decide whether that beam is, whether that cross section is effective in resisting the bending or not. So based on this Z only, we came to know that I section is the best efficient section bending. Yes or no? Tell me. So that we have discussed in strength of material, the same concept. So now based on the same format, So tell me the format here, MD. So here it is a design. So in design we have to take the factor of safeties, and that too, as I said, mostly the structural steel fails by yielding and connections fails by rupture. So obviously the stress to be considered here is Fy. Agree or not? And whenever we are going to use Fy, the factor of safety to be adopted is 1.1. Agree? So this is the stress and Z. So here this is, if it is a working stress method, simply we adopt that formula F into Z. But here it is a limit state method. So the loads are heavier than the working stress method. So obviously we have to take some factors, and we should not take completely Z. Why? Because here we are having two types of jets. If it is strength of material, then we are having only one jet, that is elastic section modulus. But this is the limit state method. So we are having two jets. What are those two jets? Section modulus, elastic section modulus, and plastic section modulus. So now the jet cannot be taken directly. So that can be taken like this, one factor beta B into jet. So this is the design bending strength. So this is the design bending strength. So now let us see what is beta B. So everything is known as ZP is nothing but, what is ZP? Plastic section modulus. ZP is nothing but plastic section modulus. And Fy is the yield stress, and this is the factor of safety. So now beta B, where? Beta B is equal to 1 for plastic and compact section. For plastic and compact section. Okay, so before this, beginning of the design of beams, we have discussed the classification of sections, that is plastic, compact, semi-compact, and slender. And we have discussed in detail so how that classification is made, okay, based on which criteria. So now for plastic and compact section, beta is equal to 1, beta B is equal to 1. Then if you keep beta B, then here it is simply ZP. So then what is the MP value? MP value is equal to some ZP into stress Fy. Agree or not? So that is it. So if the section is plastic, then it is called as MP. So this design bending strength is nothing but MP. Whether it is a plastic or compact, that is what we have discussed in plastic analysis. Clear? Now, beta B is equal to ZE by ZP. So what is ZE? Section modulus or elastic section modulus. So normal section modulus or elastic section modulus and plastic section modulus. So if you substitute here, ZP will get cancelled. So now finally we are going to get ZE into Fy into 1.1. So now this is for semi-compact section. Semi-compact section. And that too I have made it clear in yesterday's class itself. Usually rolled steel sections. Okay, usually rolled steel sections, never slender. Okay, slender sections means those are built up sections. Mainly the best example is plate girder. So we are going to design plate girder by considering it as a slender section. So for the rolled steel section, there is no formula. Okay, for the rolled steel section, there is no such case of slender section. So no need to discuss about slender sections in this design of beams. So design of beams means we are going to use rolled steel sections, means which are manufactured in the industries or various steel plants as a beam. So for that, these are the formulas. But if it is a slender section, then it is a built up. It is not a rolled steel section. It means it is not manufactured. We, as a civil engineer or as a site engineer, we are going to manufacture it. Agree? Like a plate girder. So this is the low shear case. So design bending strength in low shear case for the rolled steel section. So if it is a plastic and compact, then obviously this MD is equal to MP. And if it is semi-compact, beta is equal to simply ZD. That's the same formula. There ZD is nothing but elastic section modulus. So this is for in low shear case. So take it down. So case 2. So case 2 is the I shear case. So I shear case. We know what is I shear case. If V is greater than 0.6 VD, that is I shear case. So this is the condition. And if you interpret it, so in this case, we are going to assume that only flanges are effective in taking bending moment. So now in this design bending strength. Okay, design bending strength in this case is considered as MdV. Okay, design bending strength in I shear case is considered as MdV. So now MdV is equal to the formula MD minus beta into MD minus MFD. Agree. So this is the formula. So this is the formula for design bending strength in I shear case. Now let us see what is it. So MD is known to us. So MD is nothing but what we have discussed in previous case, that is MD. Okay. So the MD formula for low shear case is same here. So that is MD. Now coming to beta. So beta is a factor which is equal to, so beta is a factor which is equal to 2V by VD minus 1 whole square. That is beta. So beta is equal to 2V by VD minus 1 whole square. Now MFD. So MFD is nothing but design plastic section or design plastic moment, you can say design plastic section moment or plastic moment of a cross section excluding shear area. That is web. So MFD is nothing but design plastic moment of a cross section excluding shear area. So obviously shear area is nothing but web. So this is the design bending strength in I shear case. So take it down. Okay. So now if you see here, here we have to go for one check. Okay, in both low shear case and high shear case, we have to go for check. So what is that check? Let us see. So now design bending strength in low shear case MD. So we represent with MD. So MD is equal to, what is the formula? Beta B ZP Fy by 1.1. Agree or not? So this is the formula. So this should always less than or equal to 1.2 ZE Fy into 1.1. So if it is a simply supported beam, then this value MD should always less than or equal to this value 1.2 into ZE into Fy by gamma m naught, but I am directly taking as 1.1. Okay. For simply supported beam. And the value MD should be less than or equal to 1.2 ZE Fy by 1.1. This is for cantilever. This is for cantilever. So this is in low shear case. In high shear case, the design bending strength we are going to represent with MdV. So which is equal to MD minus beta MD minus MFD. So this should be less than or equal to 1.2 ZE Fy by 1.1. Okay. So in I shear case, there is no two cases like for simply supported beam and for cantilever. For all the cases, this MdV should be less than or equal to 1.2 ZE into Fy by 1.1. It means after calculating this MD, so we have to calculate this value also. So this MD value should be less than or equal to 1.2 into ZE into Fy by 1.1 for simply supported beam, and less than 1.2 into ZE into Fy by, sorry, this is 1.5. Sorry, this is 1.5. For cantilever, it is 1.5. So we have to do this check. So this is as per IS 800 2007. That is limit state method. So take it down. Okay. So this is about the design bending strength for a laterally supported beams. So after this, we are going to discuss laterally unsupported beams. Okay.